Just hold on, I'm with you. Okay, so now here is exactly the same thing, right? We gave you examples of a pitcher, of a baseball player, you know, throwing heads and tails, but could we, you know, what are we in here? We're in business, right? So if we produce chips, are some of the chips going to be good, some of the chips going to be bad, and should we know that if there's a certain number of bad chips that we should throw the whole batch out if we do, you know, some quality control, random checking of these type of things? So again, we want to know here what's the probability that there'll be 2 defects in this, right? So we have microchip production, sample of 4 items, batch 20% of all microchips are defective. You know, so we make them, we know there's 20% are defective. What's the probability that each batch will contain exactly 2 defectives, right? So exactly 2, you know, here's where your 2 comes from, right? Where does your 20% and 80% come? Because here in the batch, 4 items, 20% are defective. There's your 20%. What's that have to add up to? You know, where's this 2 come from? Here, right? And n minus r, 4 minus 2, right? Again, like I said, it's easy. You know, we could go back and forth. You'd have me so messed up I wouldn't know what's going on. But if you take the time and go and substitute it in there, you'll be able to see that it does work out. And again, we could then say, what's the chances that it's less than 2, and then what's the less than or equal to 2, and what's the chances that it's greater than 2, and what should that add up to? 1, right? So here, what do we get up here? 18% if it's greater than or equal to 2, 18%. Chances that it's less than 2, 81.92. Anybody got a quick calculator? What is 81.8192 plus 0.1808? Does that come out? Yeah, right. So again, we're just trying to get a statistical handle on how many defectives we are and whether we should throw it out or not. You can come up with any kind of an example that you want to. Here again, we're going to flip a coin, whether it's heads or tails. If it's heads, which bucket are we going into? Bucket 1, yeah, right? If it's tails, which bucket are we going to go into? Right? Now again, you know, this is deterministic because in a priori we know that, you know, we can't get into this bucket 1 unless we get ahead, right? And these also are events that are dependent upon each other. They are dependent events. See, this stuff really isn't that difficult, right? You could take woodworking and make it difficult and have people fail if you wanted to, right? If you look at it, it's really not that difficult. So here again, you're going to have the occurrence of one event affecting the other. The heads and the tail affects which bucket we're going to go into. So the coin toss, you know, you don't believe that, send, who was a running back for the Steelers? Out to call, and he'll say head, tails, both, and then they get all screwed up there, right? So you know that whether they won the game or not depended upon the call that he made here. If a tail occurs, 1/6 chance of drawing a blue ball. Why is that? Well, again, the tail, how many blue balls are there here? 1, right? Blue, red, 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 red. So there's a, now again, you said you found a mistake in the book, you know, so be careful. You know, just, we're assuming that the book knows what the hell it's talking about because you paid a couple $1,000 for it. But you can't make that. So, so again, you know, here in the probability event, drawing a blue ball dependent upon the flipping of the coin. That's all we're saying here. So again, probability of a head, 50%. Probability of a tail, 50%. Now let's go through, and what are the chances of getting a red, a white? You know, so if I flip it and I get a head, so here the conditional probability, it's conditional upon what? Conditional upon the flip of the coin. So the probability of getting a red ball, given that I threw a head, is 33%. The probability of getting a white ball, you know, dependent upon the fact that I threw a head, is 67%, and so on and so forth, right? And this is how, you know, this is the long hand of that. And if you go back through, you'll see, you know, again, there's 50%, 50%. That's where these are all from. And then there's, you know, 1/3 of the balls here are red. So 1/3 times 50% chance that I had a head or a tail gives me 0.165. So the probability of a red ball, given that I throw a head, is 0.165. The probability of a white ball, given that I have a head, is 0.335, right? like I said, go through it. It's go back through, take each one, and it's pretty. Actually, this slide does that for you, right? So here, 50-50 chance. Again, why is there a 33% chance, right? Because there's 6 balls and 2 of them are red, right? So that's 2/3, or one of them's red, so that's giving me 1/3. So here again, this is how we got those numbers. Anybody want to throw anything at me? Brick? Anything? Anybody totally lost? Anybody a little bit better off than they were before they came in here tonight? Yeah, okay, so thanks. You know, it does help when you give me positive reinforcement, because, the old guy needs that too, and I mean, and I hate like hell to be leading you guys over the ledge here and we're all going to tumble in the river and drown, right? But if you go through all this again, we said that this has to add up to 1. So if we go back through and all these, the probability of a head is 0.5, the probability of a tail is 0.5, it adds up to 1. These probabilities with these, with the red, they're marginal ones because they depend upon, the tossing of the coin. But the 0.580 and the 0.420 that has to do with the red and the white balls, what's that going to add up to also? 1, right? So in both cases, if we add up the coin flips, they add up to 1, the probabilities, and we add up the, probabilities of red and white and blue balls, those are going to come out the same way too. So this is called Bayes analysis, and again, if I died today, what would I be worth? Probably nothing. I have a couple of papers I wrote, and one is just going to come out in Expert Systems with Applications. It has to do with supply chain management, and it had to do with back orders. And we went to the, there's national identification numbers, and every item the DLA has a unique identifier. If it's a screw with a recessed head and a screw with a round head, that's a different NIN. If it's made out of titanium, that's a different number for it. If I have a hose and it's 6 feet long, that's 1 NIN, and if it's 8 feet, that's another number too. So there's millions of these NINs out here. And what we did is we tried to come up with triggers, things that would tell us whether it would be on back order or not. We'd figure out what caused to be on back order: long production lead time, long administrative lead time, environmentally. We have a lot of them, but they're made out of lead, and they're sitting in a warehouse, but the government won't let us use them because lead's illegal to have it in the solder, those type of things. So we came up with like 20 different triggers, and we used this Bayes analysis of these different categories, and to determine whether something was going to be on back order or not. If it was less than 90 days, it's not on back order. Between 91 and 180 days, it's iffy, and greater than 360, it was on back order. Again, if you want to read that paper, why, there's another example of something that you could write, or how you could take this type of management science and apply it to a real-world situation. But, and again, you have these conditional probabilities, but once the conditional probabilities is that it's stocked or it's not stocked. But then if you can give me some of these other probabilities as to whether it's one of these triggers or not, this can give me some posterior probabilities that give me a higher percentage of being accurate. So there's conditional, and that's the first part of the Bayes, but the second part of it is the posterior probability, and these are altered marginal probabilities because I have a little bit better information, right? Like I said, is global warming occurring? Well, so we say, well, there's more carbon dioxide being put out by the cars. Okay, so maybe that's occurring. But then we start looking at other things. Is there more? Is there a wobble on the Earth? Is there a variation in the sunspots? As we get more and more information, our posterior probabilities are going to be more accurate, right? Like I said, deteriorating. I wish I was in marketing management. How long's the universe been around? 12 billion years. 12 billion years, right? How long's the Earth been around? 6.54 billion years, right? Now, you want to take the last 200 years and look at the climate change, and you think you're statistically significant, huh? There is evidence of alligators in the Arctic Ocean. I'd say we had some global warming at one time. If you had alligators in the Arctic Ocean, you think it was a little warm? Yeah, you know, every 10,000 years you have an ice age.